getting to know the band induced by pz orbitals from this site in the graphene lattice, which had these translation vectors on hexagonal lattice, group 17. And we said that the symmetries are C3, C2, and M11 bar of the full space group plus translations. So G is R times translations, where R belongs to these. We said that the site symmetry group of this guy, which we called the Q1 2B position, which belongs to the same Wyckoff position as the Q2 2B position, the site symmetry group of this guy was given by C3 times E2 translation, because C3 takes it here, and then you have to translate it by E2, and M11 bar 0. And of course, for spinless, this is it. Well, also the identity, which is just this squared for spinless. But for spinful, this squared to -1. So we gave this a -1 element, which is just a 2 pi spin rotation. And we also gave the matrix representatives. We worked out the matrix representatives of these guys. Okay? And I think that what we did was we said this is I 2 pi over 3 times sigma z over 2. So pi over 3 times sigma z. And this was what? I sigma y? Was that what we gave last time? Okay. And this was minus, this was the identity in the representation, and this was minus the identity. Okay. And then I asked, how do we get a band from here? And then I was trying to write down, to derive things until I realized that I'm going to run out of time if I derive things. And I decided to give you a formula, which I'm going to rewrite here. But basically, is just inducing. So this is one representation called row 6, I think. How do we call it? Row 6 of 2B? We called it row 6 of 2B, and it's a representation of the symmetry group GQ1 of 2B, which is isomorphic to C3V. Okay? If I have the site symmetry group C3V, then I said that you can find a coset decomposition of the full space group, which means I can write the full space group as translations plus cosets of this guy. So let's find it. The way you usually find a coset representation is you try to write. So a coset representation just means that I can write this group G as some union of elements G alpha times this group, the subgroup, the GQ1 squared, times translations, which I'm not going to put here. Everything is implied. This is a space group, so some translations, translations are implied. These G alphas are, in this case, alpha goes from 1 to 2. G1 is the identity. It just gives you the full C3V. And G2 is C2, which is the one not contained in GQ1 2B. Okay? So once I have a group and a subgroup, I can form a coset decomposition of that group into the subgroup plus elements. And these are called coset representatives, G1 and G2. G1 is, there's always an identity, right? I can write G is C3V, and which is the identity. This is this full group. Its identity times C3V, and C2 times C3V. This is C6V. So this is the coset decomposition, and these elements that you're multiplying the subgroup by are called coset representatives. And they form, this is all the information you need to derive the representation, the induced representation. So now what we're going to do is derive the induced representation, row 6 of 2B, induced to the full G group. This is a representation of C3V. This is going to be a representation of G. But since we've got translations, if we didn't have translations, this would be a very simple task. If you have translations, it's also simple. It's just more cumbersome. I'm going to give the expression this, we call it, this representation is called rho G. It's got a momentum because I Fourier transformed. I'm going to express it in Fourier space. And it's got some indices, J, beta, and I alpha, where alpha and I and J go from 1 to the number of, to the dimension of the representation of this. So dimension n, call it NQ, where NQ is dimension of row 6 to B, in which this case, in this case being what? What's the dimension of row 6 of the representation of the site symmetry group that I'm going to try to induce? 2. Very good. And this guy goes from 1 to n, where n is the multiplicity of the Wyckoff position that I'm trying to induce from. In this case, that is what? Also 2, just a coincidence. That doesn't, there's no relationship between these numbers. Okay, so I said that this is, I have this representation, and I need to put representation. The representation takes a value in every element of the group. So this is J beta I alpha. Okay, so for each element of the group, I'm going to get another matrix, just like for each element of this group, I got another matrix. So this H here belongs to G, the space group. So H can be written as rotation times the translation. Okay? But I'm only going to be interested in the rotations mostly. So let's write it down. This is IRK. This is a vector. Rotated, the K, you take the vector at K, you rotate it by this R matrix. Then you vector into this 2T beta alpha. And then you take rho, this is this rho 6 2B. This is whatever representation you're trying to induce. This now has indices only J and I because it's just the indices, it's just the indices of these matrix, right? It just goes from J and I go from 1 to the dimension of the representation. And here is a group element, G beta minus 1, identity and translation by minus beta alpha, H G alpha. Okay? So let's parse this expression by doing an example. And I also gave you that T alpha beta. Let me just do it. T beta alpha. So you can deduce this. T beta alpha is H Q alpha minus Q beta. These are vectors, right? These are positions. So for example, this Q1 here is 1/3, 1/3, 1/3 E1 plus E2. Let's do the example and just induce this representation. And you'll get more feeling for what this gives you. Where the hell is this? Okay. Okay. So this is the generic expression that works for every element H of the space group. Okay? And this full element better be in what group? This is a group element. Okay, because it's just a very big group element. For H in the space group, this group better belong to which group? This is a representation. All I know is the representation of the site symmetry group. Okay, I'm trying to induce a representation into the space group, but all I know is the site symmetry representation. So this group element better belong to what? The site symmetry group. So this group element better belong to GQ. How did I call it? GQ1 2B, which is C3V. Because that's all I know. I don't have, I know this representation. I'm trying to see what representation it induces into the large symmetry group. By the way, you can prove that if this is true, this is a representation. So you can prove, representations just satisfy the group multiplication, and you can prove that if this satisfies the group multiplication, this will satisfy it, the group multiplication. If this satisfies the group multiplication in the site symmetry group, this will satisfy it in the full group. So that's why it's called an induced representation. Let's just do it and let's just do it quickly. I'm going to give you this expression for one element and show you how to compute it, and then you can give it for the other ones. Okay. Well, I'm going to give it to you for two elements. So first, let's take H belonging to C3 times no translation. Okay? So you can see that C3 times no translation doesn't belong to the site symmetry group, but it almost does. The rotation part does, right? Yes?
Sorry, just it's slower. This site representation, the first part is the...
This is a phase.
This is a phase that gives you, like, when you can switch positions.
That's right.
You want to be able to switch positions. And the second part is your representation of your site symmetry group. So
the second part is the representation of the site symmetry group, exactly. But it's got these indices. So you see, the indices are mixed. You just, it's not a full, it's not like a phase just times something that doesn't depend on alpha and beta. You see, the alpha and beta, so the structure of this guy is going to have a lot of zeros. In particular, for any H that's not part of the site symmetry group, this alpha cannot be equal to beta, for example. So it's going to have a lot of, it's going to take, so the point is, once you have alpha, given alpha, so I run through the columns or through the whatever rows. I am going to find a unique beta such that this belongs to this group. There's a unique, so it's just, that's how coset decomposition works. Basically, that's coset decomposition of groups. Okay, so let's just do that. So I'm going to choose this one at the beginning. I want to find out the induced band representation of rho G of C3, 0, okay? And I urge you to check the following, so this is H, the following relations. C3, 0, 1, which belongs to the site symmetry group, is equal to C3, 0 times identity times E, 0, 1. Well, this is pretty obvious, right? This is identity. Okay, E, 0, 1 is just this part. Okay? 0, 1 means translation by E2, right? And this is translation by nothing, 0, 0. 0, 1 just means that translate by E2, right? Is this an obvious relation? C3 plus a translation is equal to identity plus a translation. 0, 1 means translation by E2. Times identity times, this is, we can call it E0, identity. You can call this E0, that's identity, times C3. That's an obvious relation, right? Okay. So it's an obvious relation. This belongs to the site symmetry group. Okay, so let's not take E0, let's call it identity. Okay, identity here. This is identity plus a translation. Then here we've just established that you can see that this is exactly this, where G beta, this is, I've put this exactly in this form, where G beta is identity, G alpha is identity, and T beta alpha is minus E2. Is that clear? This is just this form. Yes? Yes. C3, no translations, 0, 0. I translate by 0, 0. Very good. Okay, identity. So I'm just parsing this expression. This is the same as this guy, right? So I've just found the 1, 1 element, right? G beta and G alpha equals to I means G is equal to G1, right? So this means beta is equal to 1, and this means alpha is equal to 1. In this coset, the alpha and beta have to belong to these guys. Okay? Is that clear? So I just found a 1, 1 matrix element. So let's find it, rho G of C3, 0, 1, 1 is equal to the phase. You see T beta alpha is minus E2. The phase is minus E2, so it's e to the I R K times E2 times the 1, times the representation of, so this is 1, 1 Ji. So this has indices, this is alpha and beta, and this is indices Ji, times the representation rho 6 of 2b of Ji, but that's of this matrix element, but that's just I pi over 3 sigma z. Is this clear where I got this from? Yes.
Like to see that the T alpha beta is minus E2, I see it because like I need to multiply the E2 to the 0.
Well, this is this.
Okay, so it's just in different position there.
Yeah, I just put it, yeah.
Okay.
Because it's identical. I know,
but like just.
Yes, just for visual, yeah. This is this.
Okay, and then I can put the C3 in front, and then the C3.
This is H.
Okay, yeah, right. Okay, yeah. Mm-hmm.
This is identity. This is identity. Make sense?
Yeah.
Okay. Yes? Very good. So I just took these indices 1, 1. I get that. And Ji is just this matrix, which I just took it from here because this full matrix element now is C3E2, which I know the representation of. Okay, so let's just make this. Now let's find the 2, 2 matrix element. So I want the 2, 2 matrix element in alpha and beta. Okay? And for the 2, 2 matrix element, I urge you to check the following, that C3 E2 is can also be written as C3 0, 0 times C2 to the minus 1, times C2 times C2 to the minus 1 times translation by E minus E2. Okay? This is an identity, a group identity. This element is H. This element is G alpha. This element is G beta. So G beta is equal to C2. G alpha is equal to C2. And T beta alpha in this case is E2, not minus E2. This you can just check by group, by just, you know what C3 does is it takes this and this. Okay, this is just a group relation. You know what C2 does? It takes all E's into minus E's. Okay, so you can check that. But I can tell you it's true. So this means alpha and beta are what? Since they're C2, what are they? Alpha and beta. Since G2 is C2, and G alpha and G beta are also C2, what are alpha and beta? 2. So I found the 2, 2 matrix element is e to the I with a minus, because beta alpha was minus, RK E2, times the representation, the same representation of C3, times e to the I pi over 3 sigma z. So I found the induced representation, at least for this for this group element, the induced representation of C6 of the row 6 representation into G for the group element C3 is diagonal as it should be, and it's e to the I C3k E2 0 0 e to the minus I C3k E2 times e to the I pi over 3 SZ. This is tensor product. So it's a 4 by 4 representation, right? Two matrix elements, each a matrix, so 2 by 2. This is 4 by 4. Is that clear? If it's not clear, tell me now. Yes.
So like we found, we took the same group element, we found two different decompositions.
You took the same group element just without the translation. Yeah. So you took the same group element here.
Yeah.
You know, the logic is reverse. You take H, and you try to write an expression so that this guy belongs to the side symmetry group. And I was able to write it, and this is the expression. But the logic goes, you pick the element H, which I picked it, and try to write this expression so that this full guy belongs to the side symmetry group. And that's how I've done it. That's the logic. But this decomposition is unique. You can only write down one. Once you pick G1 and G2, there's only one way to write this. So I pick this. You pick H, and you want to find alpha and beta. Okay, so that you want to run through alpha and beta because you want to form the full matrix. But given one alpha, the beta is unique. Okay. So you just run through all the indices of the matrix, and you form all these things, and then you find what the alpha is, what the beta is. For example, there's no 1-2 matrix element. There's no way of. Okay. Very good. I can do the same thing with the mirror, and I'm not going to do it, but it's done in the notes. Okay. And this gives me ISY 0 0 minus ISY. It's also a 4 by 4. Notice that these rotations, at least the rotation part, this is C3 with no translation, also belong to the side symmetry group. They belong to the full space group, G, but they also belong to the side symmetry group. The way you see that in the induced representation is diagonal for both of these, right? Just in each block. Now, let's take an element which doesn't belong to the side symmetry group, and this element is C2. So I took H, which does not belong to the side symmetry group C3V, and all these elements which don't belong to the side symmetry group will be off diagonal. So you can go through the same procedure and find out that the only matrix elements that you get are going to be off diagonal, and this is 0 minus I 0, and this is a 2 by 2 I. Okay? So moral of the story, when I induce from some representation to the full group, the elements that belong to both the full space group and the side symmetry group or the subgroup come with an induced representation which is diagonal. The elements which don't, which belong to the coset representatives, C2, for example here, come with off-diagonal matrix elements. Okay? I leave you to check that this is a representation of the full group. I gave you representations of 1, 1, of C2, and of C3. I gave you representations of the C6V. It's a representation, and it's called the induced representation, and we wrote it down here once and for all. And this is the band. This is the band representation. It's actually an elementary band representation, which I'll define right now. But band representation induced by spinful PZ orbitals sitting on the A and B sublattices. A and B sublattices are just the Wyckoff position 2B. 2B Wyckoff in graphene. Okay? So that's what these guys are. All right. So now comes several things. Thing number one. So that's how you define the band. Okay? I don't want to define it through energetics. That's a band. That's an electron band. It does depend on K. It's just a representation. Now, why is this good? Well, you have several things that you can prove about induced representations. I want to find out the most elementary band, the representation that cannot be decomposed in other representations. So normally representations can be reducible or irreducible. A band representation, which is just an induced representation, can also be reducible or irreducible. So now I can employ mathematics to just see when the band representation is reducible and when it's irreducible. So for example, if I have rho 1 plus rho 2 representations of some subgroup of the site symmetry group and induce them in the group, this is rho 1 induced in G plus rho 2 induced in G. So you can see that an induced representation is reducible if the representation of the subgroup or of the site symmetry group is also reducible. Okay? So that means that I only need to consider irreducible representations of the site symmetry group, which we have implicitly done. But you can ask me, why do I need to consider only a reducible representation of the site symmetry group? Well, the reason is this. If I don't consider a reducible representation of the site symmetry group, the band is a composite band. So I would take, I could just separate that band into two other representations. Okay. It's also, I don't know, it's a representation induced in the subgroup of a group. Okay. Is the same thing as the representation induced in the group. Okay, this is identical. If H is a subgroup. And this basically shows you why we took only the maximal Wyckoff positions. The maximal Wyckoff positions are positions that don't have a subgroup, whose site symmetry group doesn't have a subgroup in between them and the full group. And the reason is this. Because if it had a subgroup, I could first induce to the maximal one and then induce up to the group. Okay, so this tells you that I only need to consider maximal Wyckoff position, which is also have done implicitly. Okay, because if this was a representation not of a maximal Wyckoff position, I could first induce to the maximal Wyckoff position, because then there would exist, if this was a representation of a site symmetry group which is not a maximal Wyckoff position, then there would be a group, subgroup H, in between the site symmetry group and the space group, but I could first induce to H and then induce to the full group. So I might as well just induce from the maximal Wyckoff position. And we've done these implicitly, but this is the reason why. It's just representation theory. And now comes the physics. The physics tells you that so when you do this, these are called elementary band representations. That's actually not entirely true. You have to check for a super annoying set of exceptions that I don't need, we don't have time to go through. That basically, takes a few months. But let's go. We don't consider those. So these are called elementary band representations. And elementary band representations are representations induced in the full space group from site symmetry groups that are maximal, and the representation that's induced is irreducible. Okay? And what this gives you is it gives you the following theorem. It tells you that elementary band representations are either connected in the Brillouin zone, or if they're disconnected, they're topological. So let's understand this. So, I'm going to make a theorem. I'm going to sketch the proof basically. I'm going to sketch the proof that it's okay. So let's say I have this band. This is just this representation. Some representations are just bands. So as I go through the Brillouin zone, I have bands that connect like this. Okay? And let's say that these two form an elementary band representation. I don't care how many I have. Here I would have 4, but let's say I have 20. But if these form an elementary band representation and there's a gap between them, so they say that these form a elementary band representation rho, which is a representation of the full space group. If there's a gap between them, then what I can do is I can take a projector and project into these bands and project into these bands. And fundamentally, projectors, when I have a gap, are local. So I'm able to derive a Hamiltonian, which is just the full Hamiltonian projected into these bands, plus the full Hamiltonian projected into these bands. And that's going to be a local Hamiltonian, each of them, because the projector has a gap. But if it has a gap, and I can write a local Hamiltonian into these bands, then it means that these bands were also induced from some representation of a side symmetry group of some local orbitals. Because I said, that a set of bands can be induced from local representations of orbitals. So this, if there's a gap, and this is 1 plus 2, then this means that my elementary band representation is rho 1 plus rho 2, which is a representation of these bands plus representation of these bands. If rho 1 and rho 2 come from localized orbitals. Localized orbitals was certainly something that I assumed everywhere through because I built things from the atomic orbitals, which are localized. But this would mean that rho is not elementary. So I have a contradiction. So one of two things must be wrong. Either, one, bands are connected, there's no gap. Bands in an elementary, electron bands in an elementary band representation are connected. Or two, either this set of band, well, not either, both this set of band and this set of band cannot be described by localized Bani orbitals. If it's disconnected, so I made the assumption, I said these two bands form an elementary band representation. I can split them, say I can split them, then if I can split them, and this is local and this is local, and these are both described by local atomic orbitals, then both of these form band representations, but then my full band representation is sum of this one plus this one, so it's not elementary anymore, so either one of two things must be wrong. Either I cannot put a gap here, separate them, or rho 1, rho 2 are not described by localized Bani orbitals. And this second one means they're topological. This is the definition of topological. Right? So, topological bands are not elementary band representations. They cannot be, because elementary band representations can be described by localized Bani orbitals. And if an elementary band representation comes disconnected in a set of bands with a gap, then each part of it has to be topological. So this if I put my Fermi level here, if it was disconnected and I put my Fermi level here, I would know that this is a topological insulator. Okay? So that's the power of this method, that basically you induce a representation and now you ask, well, this is an elementary band representation. If I induce it from maximally localized or from localized orbitals, like that one, that is going to be connected. So that's connected. But if I find one that's disconnected that is similar to this one, then it cannot be induced from maximally localized Vanni orbitals, because the only one that can be induced is that one, or from orbitals on sites, and then it means it's topological. Okay? Okay, so now let's find what. So now I'm going to ask, what are the phases of PZ orbitals in Wickel position 2b in graphene? Okay? So I'm going to claim that this is one phase where you have the band representation, the elementary band representation that's connected in the Brillouin zone, but there's another phase that you can immediately find. And before I do this, I want to find out what this band representation does at all momentas in the Brillouin zone of graphene. So now I'm going to say, go away from real space, so no more real space, go to momentum space. Okay? And the momentum space Brillouin zone is this guy. And the momentum space Brillouin zone has several points in it which are special. So for example, the K point is special, the gamma point is time reversal invariant, and it's got 3 M points which are also special because they are, so this is, they're time reversal invariant. So time reversal invariant, time reversal invariant, time reversal C3 invariant, and K prime. There's 2 K points. Okay? So now I have this band representation. This is the band representation induced from localized PZ orbitals. And I'm going to ask what it does. I'm going to ask what this band representation does in the Brillouin zone. I wrote it as a function of momentum for particular reasons, just to see what it does in the Brillouin zone. To be able to, connect this to more kind of, to the spaghetti of bands that you see in ab initio, or like in plots of band structures. So I'm going to plot this as gamma K M. And this is an arbitrary axis, call it energy, but I don't have any information about energy because I don't have a Hamiltonian. What I do have information about is the band representation. So I know what the electrons from PZ orbitals do as they go around the Brillouin zone, and I'm going to find out what they do at high symmetry points in the Brillouin zone. So that is representation subduction, again, because I have all that they do in all K. This is rho 6 2b induced in G. But now I want to subduce it to some groups of some K points in the Brillouin zone. This is K, this is big K, okay? K point in the Brillouin zone. So I'm not going to write these points. This is obviously the gamma point, the 0, 0. These are, 1/3, 1/3, 2/3 in units of G1, the reciprocal lattice vectors, G1, G2, big G1, G2. Obviously there's a bunch of G's here. This is not the same as this. This is a unit vector, call it whatever. Reciprocal 1, reciprocal 1, reciprocal 2. Okay, all these points you can find them by geometry, right? But all you need to do now is take this band representation and subduce it to points in the Brillouin zone. So let's just do this for the K point, in the Brillouin zone. So what is the what is the, not site symmetry, what is the symmetry group of the, so we're in momentum space, no more site symmetry. We have the band representation of momentum space. What's the symmetry point of the big K point in graphene? What's the symmetry group of that big K point? What do you think it is? C3, C3V. So the symmetry point, the symmetry group of the big K point in graphene is C3V. We know the representation of C3V. We found them. What are they? Can somebody tell me? The double representation. There was E. Can somebody go back and tell me their characters? C3, mirror, E bar. We had row 4, row 5, row 6. These were site symmetry, but they were just representation of the symmetry group, so it doesn't matter. Can somebody tell me their characters? What were they here? C31, 1, 1, minus 1.
It's 1 minus 1, 1.
Uh,
1 minus 1, 1.
Like this?
Yeah.
Okay.
And then it's minus.
Which one is it? Minus? It's got a square to minus 1. 1 second. So it's minus 1, minus 1, minus I. Okay. There's a minus 1 here too. Okay. Okay, good. Okay, and this is 0. Very good. Hang on, actually. Okay, there's something. Okay. Okay. So now I want to know what this representation does when I what this band representation does when I subduce it to here. So all I do is compute its traces. Trace of rho GK. These are the traces. And you're going to find out, if you compute the traces, you're going to find out that the traces are what are they? 1 second. You're going to find out that they're E bar, C3, 4 of E, minus 4. You are going to find this is minus 1, and this is 0. Okay? So these are the traces, and I've told you that representation decomposition is unique, and there's a theorem that tells you that you only need the characters, and basically when you add things, the characters of this, the way this representation, rho G of K, when subduced to G of big K, decomposes into representation of C3V is, you can find it just by characters, and I claim that this tells you immediately that this decomposes in row 6 plus row 5 plus row 6 plus row 4. Okay, because you have 1 plus 1 plus 2 is 4, minus 1 minus 1 plus 1 is minus 1, minus 1 minus 1 minus 2 is minus 4, I minus I, 0, 0. The characters match. All you need to do is basically the characters form kind of a linear space, and all you need to do is 52 is just check this, and this decomposes in row 6 plus row 5 plus row 4, and the only thing you need to find out, you need to draw here, is their dimension. So the dimension is, this is row 4, it's one dimensional, this is row 5, and this is row 6, it's two dimensional. Okay, so that's what this band representation does at this point, at this K point. I can go now to all the other points in the Brillouin zone, gamma, M, and decompose this representation, this band representation, into representations of these points in the Brillouin zone. Okay, So gamma has symmetry group what? C6. And all I will need to do is decompose this band representation. So by the way, when I add it here, I have to put the k equal to this k, right? So I have to, when I subduce it here, I have to add in the band representation. In the k here, I have to add this k. Okay? When I go to gamma, I add the gamma, the k of gamma, so 0. So that's why this band representation changes as you go through the Brillouin zone. In the gamma, it turns out that there's two representations, gamma 8 and gamma 9, both two-dimensional. And why do they have why do they have to be two-dimensional? Why all the representations have to be two-dimensional here, if I have time reversal? Kramer's degeneracy. And at M, it turns out, since it's C2, the symmetry group of the M point is what? C2? C2V. And C2V has only one two-dimensional representation. It's called M5. Call it whatever. It is two-dimensional. M5, M5. And here you're just stuck because, there's no decomposition, there's no choice. You basically, it has to work out that this M5 plus M5 because it's a four-dimensional. This band representation is four-dimensional. Okay? Actually, let's do this. Let's put this row 6. So since I don't know what the energy is, because I don't have any information about the energy, I can put this wherever I want to. Okay? So this is what you'll see in an ab initio plot. You'll see that, induced from pz orbitals on the 2b sites of graphene, when you go to the Brillouin zone, only these representations appear at high symmetry points. Okay? There's other representations that don't appear because they're not inducible from pz orbitals. Okay, so forget about, these are the representations that show up at high symmetry points. But I can now go to high symmetry lines. Okay, so for example, I can go to this line or to this line. Okay, in the Brillouin zone, and ask what happens on this line, which would be this line, and what happens on this, or what happens on this line, or which, M is M and M prime. You can call this M prime if you want. Or what happens on this line, for example. So I can go like this from these points and ask what happens there in the Brillouin zone. And you'll find out that this band representation transforms into representations of these lines. Now, I will tell you that the symmetry group of these lines allow only one-dimensional representations. You can go through them. And the symmetry group of this line allows representation lambda 1, lambda 2. And the symmetry group of this line runs representation sigma 1 and sigma 2. Okay? So I have gamma, k, m point in the Brillouin zone. So I go like this. Okay? And what I want to ask is, so I know what happens at the high symmetry points in this band representation. I want to ask what happens away from high symmetry points in this band representation. And I could do this in two ways. I could say, well, I'm going to subduce this band representation to the site symmetry group, to the symmetry group of these lines. Okay? And then you'll see that rho here subduces to lambda 1 plus lambda 1 plus lambda 2 plus lambda 2. It's a four-dimensional representation. All these lambdas, which are symmetries of this line, sigmas are representations of this line and representations of this line. They're one-dimensional. So this is a four-dimensional representation. The band representation has to decompose in 4. And this is, on this line, there's only also one-dimensional representation, sigma 1 plus sigma 1. There's two different one-dimensional representations, plus sigma 2 plus sigma 2. So that's what it does. And that's just telling you that as I move away from this guy, around somewhere around here, I just have a set of bands that looks like this, 4 one-dimensional representations. Is that clear? So you can just go, I mean, I don't have the time to go through it, but I've showed you how to do it at the K, at this K point. But I can do the same everywhere in the Brillouin zone, since I have the representation everywhere in the Brillouin zone. So I've done it at high symmetry points, and I'm doing it at high symmetry. So this is called this lambda 1, lambda 2, lambda 1, lambda 2, sigma 1, sigma 2, sigma 1, sigma 2. Okay? So now, you know how this band representation decomposes at high symmetry points and away from on high symmetry lines. So now we're stuck. Where all that's left to do for us is to get an overall picture of the band structure, is to see how these connect to these. Okay, so I have some gaps here. I don't know what to do. And to see how those connect to those, all you need to realize is that the band in the Brillouin zone, when I go from here, which is a high symmetry point, to this line, or when I go from here to this line, okay, this line has the same set of representations everywhere. It's kind of the Brillouin zone equivalent of this non-maximal Wyckoff position. But this is in the Brillouin zone. So the only thing I need to do is find out how a representation here breaks up into representations of this line, and how a representation here breaks up into representations of this line. That's just group theory, and I can do it. And I can tell you that the gamma 9 representation of the gamma point breaks up into lambda 1 plus lambda 2. The gamma 8 representation also breaks up into lambda 1 plus lambda 2. And the M representation breaks up into lambda 1 plus lambda 2. And 5. The row 6 representation, which is at the K point of C3V, breaks up into lambda 1 plus lambda 2. The row 4 representation is one-dimensional, breaks up into lambda 1, and the row 5 representation breaks up into lambda 2. Okay? So that is just group theory, and it's just knowing the characters of this representation, which we know, or of this representation, which you know, and the characters of this one, and then I can just find out how they decompose. So now in the last, I guess, 10 minutes, there's a fundamental thing that one has to realize. And the fundamental thing is that when I go from here to here, or from here to here, right, that's moving in this direction in the Brillouin zone, in this direction in the Brillouin zone, this guy decomposes into lambda 1 and lambda 2. This guy decomposes into lambda 1 and lambda 2. This guy decomposes into lambda 1 and lambda 2. This guy decomposes into lambda 1. This guy decomposes into lambda 2. The same thing in the, sorry, this is sigma 1, M5 is sigma 1. They're just one-dimensional representation. This decomposes into sigma 1 and sigma 2. This decomposes into sigma 1 and sigma 2, which are representations of the symmetry group on this line. This guy, when it goes here, decomposes into sigma 1. This guy decomposes into sigma 2. This guy decomposes into sigma 1 plus sigma 2. Okay? Because it's another line, so it can decompose in this direction to lambda and in this direction into sigma. Yeah? So now all you need to do is to realize that bands in the Brillouin zone can connect only if they have the same representation. So in other words, lambda 1 coming from gamma cannot connect with lambda 2 coming from K along the gamma K line because they're different representations. And once I move on this line, I have the same symmetry group. So I cannot change representation in a single band moving along this line. One band has one representation on this line. I cannot change the representation, so this is not possible. And these are the connectivity rules these are called connectivity rules in, well, I don't know what they're called, but We call them connectivity rules in the Brillouin zone. So subject to these rules, let's see how many band structures we can draw. Well, it's pretty clear that we can draw the following band structure. So two-fold representation at the gamma point. Row 6, row 4, row 5, M5, two-dimensional at the endpoint. This two-dimensionality is also because of time reversal here. Lambda 1, lambda 2, lambda 1, lambda 2, sigma 1, sigma 2, sigma 1, sigma 2. That's compatible. And by the way, this is not like something that, I don't have time to go through, but you can imagine how this can be mapped into a graph theory problem. So you can just you can kind of like, these connectivity rules, you can kind of like, you can put them in on an automaton, well, on a very hard automaton, but you can basically map these into a graph problem where these are the nodes, and the graph has, edges between nodes if the compatibility relations match. So if I can get the same representation from here coming from here, then they can connect. And if not, they cannot, etc. So this is one band structure. And this is the connected four-fold connected. So in other words, you go through a Brillouin zone. If I start here, I have to go 4 times to the Brillouin zone to get back here. Okay, if I start here, I would go back here, then move up, down. Okay, it's four-fold connected through the Brillouin zone. So this is called band connectivity, it's four-fold connected. But how many the graphene has how many electrons per unit cell? So each pz orbital has 1 electron, 2 electrons, 2 pz orbitals, 2 electrons. So graphene has 2 electrons per unit cell. If bands are four-fold connected, where does the Fermi level sit? So at 2 electrons per unit cell, the Fermi level sits somewhere here. And this is a metal. And it's an enforced metal because my connectivity is 4. Bands have to come in multiples of 4 with pz orbitals, but the number of electrons is 2 per unit cell. Okay, so this is a topological semi-metal, if you want, because the number of electrons per unit cell is a fraction of the band connectivity. So being a fraction of the band connectivity, you know that the Fermi level has to sit in a metallic state. It cannot sit it cannot sit in a gap. Well, that's not entirely true. It cannot sit in a gap unless that gap is topological. And let's find the second. So this is one type of band structure, and this is the four-fold connected elementary band representation. So this is this. This is that band structure. Now, what we can have is another band structure, and the way we see it is immediate. Since I've told you these representations, the way I've put this axis means energy, but I have no information about energy. I'm just trying to find out what phases I have. Let me just do the following thing. So this is gamma 8 here. Gamma 9, gamma 8. Let me just flip this row 6. Row 4, row 5, row 6. M5, M5. I'm just going to flip this, and now I'm going to do the following thing. Okay? This is a perfectly valid connectivity in the Brillouin zone. Satisfies the fact that these representations in the Brion zone behave in this way. They subduce into these representations on high symmetry. So this is gamma point, K point, M point. Okay? This is a perfectly well-defined connectivity. But you look at it, and you see that at 2 electrons per unit cell, it has a gap. Okay? And you know then that, by what I said before, this cannot be described by maximally localized Vanni orbitals. Because if I describe things by maximally localized Vanni orbitals, or like by just orbitals, by PZ orbitals, respecting the symmetries of the lattice, I get to this band representation, which is 4-fold connected. But since this is not 4-fold connected, bands here are 2-fold connected, and there's a gap, I know I cannot describe it by maximally localized Vanni states respecting the symmetries of the lattice. And this is actually something that Solyanov and Vanderbilt, proved for the time universal invariant topological insulators, and people before them for Chern insulators. But this is basically the generalization to crystalline symmetries. The moral of the story is just what they found, that even though I have PZ orbitals, all these bands do come from PZ orbitals, they cannot be maximally localized if they're not 4-fold connected. And if they cannot be maximally localized, that immediately means I have a topological insulator, because if I put this band structure close to the vacuum, if my Vanni orbitals are not maximally localized, they're extended, it means I would have an extended state, and this extended state is just the edge state of the topological insulator. So extended states of the topological insulator, basically the moral of the story is if you have maximally localized orbitals, when you cut a system, you cannot get an edge state. An edge state is extended, maximally localized orbitals are exponential. When I cut the system, if I have maximally localized orbitals, I cannot get an edge state, I cannot get topology. So what this little exercise has showed us is that by just looking at the Brion zone connectivity, I can get 2 different sets of band structures. One of them disconnected, so connectivity 2 and another 2 bands with a gap. One of them connected. The whole point about the previous 2 lectures was to show you that if I have bands coming from localized orbitals, the only possibility is 4-fold connected, localized orbitals respecting the symmetries of the system. So the fact that I found something disconnected immediately tells you that this is topological. So the moral of the story is that at 2 electrons per unit cell, graphene is always non-trivial. The hexagonal lattice is always non-trivial. In other words, it's either an enforced semi-metal here, or it's a topological insulator. There is no trivial side of graphene with PZ orbitals on sites. Moreover, if you put sp2 orbitals, the same story happens. It's either connected or it's topological. This symmetry group, wallpaper group 17, has the property that wherever I put my orbitals, with the exception of if I put them here, in which case I create a triangular lattice. If I put my orbitals on the gamma, in the center of the unit cell, this is the unit cell. If I put my orbitals in the center of the unit cell, I can get something trivial. As long as I don't put them at the center of the unit cell, if I put them here, here, or here, it doesn't matter what orbitals they are, SPD, I'll always get something non-trivial in this sense, that it's either an enforced semi-metal or a topological insulator. Now, I'm going to finish, but basically you can run this program through all the space groups, all the Wyckoff positions, and all the orbitals, and find out which groups allow you for only non-trivial behavior, which groups allow you sometimes for trivial behavior with some orbitals, etc. So if you want to look at some of these things, they're available on the Bilbao crystallographic server for all the 230 space groups for all the Wyckoff positions. And there's many lattices which have this, there's many lattices and orbitals which have these properties. Sometimes a lattice has this property that is non-trivial both is either a protected semi-metal or a topological insulator only for some orbitals, sometimes only in some Wyckoff positions, but there's many of these lattices. The graphene lattice is very special in the sense, or the hexagonal lattices really, that they have this on for a lot of orbitals on a lot of Wyckoff positions. Okay, so thank you.